Today I'm going to be solving problem 5.37 from the book Introduction to Electrodynamics by David J. Griffith. The question has two parts, part A and part B, and I'm going to start with part A first, where we have a phonographic record with a radius of r carrying a uniform surface charge sigma and is rotating at a constant angular velocity, where we are asked to find the magnetic dipole moment of the phonographic record. So we know that the magnetic dipole moment is given by the equation magnetic dipole moment is equal to current times the integral surface area dA, where we then integrate dA to get the following equation. Magnetic dipole moment is equal to current times area, where we know the area of a phonographic record is pi r squared. So substitute that back in to get current times pi r squared. Since we're asked to find the magnetic dipole moment of the phonographic record, we need to solve for current first. Well, we know current is equal to the line charge, lambda, traveling through a wire with the speed of v. Substituting that back into our equation gets us the magnetic dipole moment is equal to lambda times v times pi r squared. However, we're running into an issue here. We see these are in terms of lambda and velocity, linear velocity, but our phonographic record is sigma and angular velocity, so we need to substitute that back in. Luckily, we know that our line charge lambda is equal to the surface charge sigma times dr, and we know that linear velocity is equal to angular speed times r. Substituting that back into the equation gets us the magnetic dipole moment is equal to sigma times omega times r times pi r squared dr. So since we're looking for the total magnetic momentum of the phonographic record, we need to integrate both sides, where we integrate dm and we do an integral from 0 to r of sigma times angular velocity times r cubed times pi dr. Taking our constants out as the front and integrating the left side first, we get the total magnetic dipole moment is equal to sigma times omega times pi, doing the integral from 0 to r cubed dr. This is a fairly simple integral, where we get the following: r to the 4th over 4 evaluated from 0 to r. Substituting r back in, we get big R to the 4th over 4 as our following answer to this integral. So we then plug that back in, showing that the magnetic dipole moment is equal to sigma times omega times pi times r to the 4th over 4. Writing this a little nicer, we can see the final answer is r to the 4th sigma omega pi over 4 is equal to the magnetic dipole moment of a phonographic record for part A. So now for part B, where we are asked to find the magnetic dipole moment of a spinning spherical shell in example 5.11, given by this figure here, showing that for points r smaller than big R, that the potential is that of a perfect dipole. Luckily, this problem isn't as bad, but we're looking for the magnetic dipole moment again, so we know it's equal to current times surface area dA. Integrating dA, we get the magnetic dipole is equal to current times area. Here, from the previous example, we are given that dq is equal to sigma times 2 pi r sine theta r d theta, where dq is a charge and we want to know current. How do we relate current to dq, charge? Well, current is simply charge over time, dt. And we know dt is the time for one revolution of our spinning spherical shell, so we can set dt to be 2 pi over omega. Setting these two up with each other, current then becomes sigma omega r squared sine theta d theta. Substituting that back in for the magnetic dipole moment, times area. Well, here we want the area of the ring again, and we are given it to be r sine theta. Well, we know that the area is equal to pi r squared, and we know our r now, the new radius, is r sine theta, giving us the following equation for area to be pi times r sine theta squared. Substituting that back into our magnetic dipole equation, we get the following new expression. It's a pretty long expression, but sigma omega r squared sine theta d theta times the area of the ring pi r squared sine squared theta. Simplifying this down, we get our new expression to be sigma r to the fourth sine cubed theta d theta. So since we're looking for the total magnetic dipole moment, we have to integrate both of these sides, where it's a spinning spherical shell. So the integral becomes 0 to pi. Integrating dm gets us the total magnetic dipole moment, m. Setting our constants out to the front, sigma omega r to the fourth, integral from 0 to pi, sine cubed theta d theta. We've done this integral a couple of times in class, so I'm not going to go over the steps for it, but this integral results to being cosine cubed theta over 3 minus cosine theta. Evaluated from 0 to pi, plugging in our things, cosine cubed pi over 3 minus cosine pi from one side minus cosine cubed 0 over 3 minus cosine 0. This all simplifies down to 4 over 3, which we can plug back into, giving us the total magnetic dipole moment to be 4/3 pi sigma omega r to the fourth in the z-hat direction. However, we have to use the multiple expansion. Get another piece of paper for this. And referring back to our figure, we know that it's pointing in the z direction, and it's at the center, at the origin. So because of those two specific conditions we're given, we can use the multiple expansion for A, which is given by this equation. A dipole is equal to mu naught over 4 pi times the magnetic dipole moment m times sine theta over r squared phi hat. Well, we know what our magnetic dipole moment is from before, which we got here. So plugging that back in, we can get the final equation that the multiple expansion for A becomes mu naught pi omega sigma times omega pi r to the fourth over 3 sine theta r squared phi hat, showing that the spinning sphere produces a perfect dipole field.